Let's get some practice solving these NMR problems that don't provide us with a spectrum, but simply list out in textual form the NMR data. So let's look at letter A to begin with. We've given a formula, C4H8Br2. And if we calculate the HDI for that formula, remember that halogens are the same as hydrogens in this case because they both occupy one bonding partner, most time with a carbon. So we take the number of carbons, multiply by 2, add 2, and subtract the number of hydrogens, subtract the number of halogens. 4 times 2 is 8, plus 2 is 10, minus 10 is 0. So we have no rings or double bonds here. The IR data is not very helpful. Basically, it tells us there are some sp3 hybridized CH bonds, which is more often the case than not, so that's not going to be very helpful for us. But we can observe the NMR data here. We've got a 6 hydrogen singlet at 1.87, and we have a 2 hydrogen singlet at 3.86. So what we can do is translate 6 hydrogens into 2 equivalent CH3 groups, and the 2 hydrogen singlet is probably a CH2 that has no neighboring hydrogens. Neither do the methyl groups. So what we have here are some hydrogens that are in their own environment, but they have no neighboring groups, and we know that because we have 2 singlets here. So we need to sort of piece things together. We know we have a bromine, we know we have another bromine, we know we have 2 CH3 groups because they have the same chemical shift, and we know we have a CH2 group. And does that account for everything? Well, 2 methyls is 6 hydrogens, here's 8 hydrogens, that's all we have in the formula. We've got the 2 bromines. We have 2 carbons as part of our 2 CH3 groups. We have 1 carbon as part of our CH2 group. That means I should write another carbon here that has no hydrogens attached. And that gives us some more information as well. Let's look at the chemical shift of these 2 different hydrogen environments. We have a CH2 that's shifted to 3.86, which is significantly changed from its 1.2 ppm standard shift, and also the 2 methyl hydrogens are shifted from a standard 0.9 ppm to a 1.87. So the bromines have some strong effect on these methyl groups. We remember that we have some symmetry. These are 2 equivalent methyl groups, so chances are they are probably on the same carbon. So we could look at a carbon that has the 2 methyl groups attached and has 2 other groups attached that are not hydrogens. Remember that these 2 methyl groups are singlets. So in order to get these methyls to shift from 0.9 to 1.87, we probably need a nearby bromine. So I'm guessing that one of these bonding partners on this carbon in the middle here is a bromine. And then if we cross off some of our pieces, you see that we have a bromine left and a CH2 left. And that means the CH2 has to be here. Otherwise, if I put a bromine there, my molecule's done. I don't have the whole formula matched, and that means that the bromine, the final bromine, is attached to that CH2. And so we can draw this molecule a little more carefully right up here, and that is what I would expect for letter A. We have 2 equivalent methyl groups that have a singlet because they are not near any hydrogens. I've got a CH2 that's also a singlet. It's not next to any hydrogens, and I have some strong chemical shifts for the CH2 and for the methyls on account of the 2 bromines. All right, let's move on to the second one, B. If we look at the HDI information, I think we're going to find that, again, we have 0 HDI. So let's look at that over here. 3 carbons times 2 plus 2 minus the hydrogens minus the bromines is, again, 0. So we have no double bonds or triple bonds here either. We also don't have any information about the number of hydrogens that each of these signals is coming from, as we did up here, okay? However, there are only 6 hydrogens, so we need to apportion them so that the quintet and the triplet make sense. So if we think about the triplet, that means N equals 2. Those hydrogens that are comprising the shift at 3.5 ppm are near 2 hydrogens. And the quintet, in this case, N equals 4, because those hydrogens are near 4 hydrogens. So what this tells me is that most likely this signal is from a CH2 and this signal is from 2 CH2s. Because these are the only 2 hydrogen signals, they have to account for all 6 hydrogens, and they are certainly going to be coupled with each other. So the one signal, the hydrogens from the one signal, say this one, which is 4 hydrogens, are certainly going to be producing this quintet on the other signal. So we can get information here because these are the only 2 signals in the proton NMR spectrum. So I think we have one CH2 that's shifted to 2.4. It is next to 2 different CH2s, 2 equivalent CH2s that are both shifted to 3.5. So we can draw a piece of a structure here where I have 3 CH2s, and there's some symmetry here, remember, because I have 2 equivalent methylenes. That would be these 2. This one in the middle should have a quintet as its signal shape because it's next to 4 hydrogens. And then, of course, I've accounted for the C's and the H's in my molecule. I still have the bromines here. That is what the X's are. And so, in fact, these should be bromines. And that's a pretty simple 1,3-dibromo propane molecule. All right, let's take a look at C now. And I'll use blue in this case. So C has a more interesting chemical formula, at least in my experience, C5H10O2. I think we'll find that we have 1 HDI here. So let's go with the number of carbons times 2 plus 2 minus the number of hydrogens. And remember that oxygen has no effect on the HDI count. And so in this case, we do get 2 over 2 equals 1. So we have 1 double bond or ring in this case. Most likely it is a double bond because we've got some more interesting IR data, which has a peak at 1740, which indicates a carbonyl. So we have got a carbonyl, either an aldehyde or a ketone, but because we have 2 oxygens, there's also the possibility of an ester as well. So I would say it's not a given that it's an ester, but it's a reasonable possibility. So let's think about that. We also have 4 different NMR signals. We've got a 3-hydrogen triplet at 1.15 and 1.25, and we've got 2 hydrogen quartets at 2.30 and 4.72. So when we have signals like this, a 3-hydrogen triplet down near the 1 ppm range and a 2-hydrogen quartet shifted downfield in the 2 to 4 range, that's typically indicative of an ethyl group. Let me draw that a little better here. Right? Or where X is something that does not contain hydrogens, we've got that ethyl group hanging out there. So it looks like we have 2 ethyl groups that are not the same, obviously, because we have different chemical shifts. The biggest indicator here is the 2-hydrogen quartet at 4.72. That's quite far shifted from a standard 1.2 ppm methylene signal. So that tells me that this is probably next to an ester. So what we have is probably an ester with an ethyl group attached to the O. So the R group in the ester is ethyl in this case. And that takes care of, most likely, these larger shifted triplet and quartets. And that leaves only one other ethyl group. We only have one attachment point here on this ester, and so most likely this is what we get with this sort of have 2 different ethyl groups that are experiencing different chemical shifts. Does this match the formula? Well, let's count. 1, 2, 3, 4, 5 for carbons. 5 hydrogens here, 5 hydrogens here, that's 10, that works. and I have two O's. So this definitely works, matching the formula for number C.